Hi, everybody. Good to see you again after a small break after the summer meeting. We're going to continue on with our climate and health theme here for September's webinar, and we're really happy to have Fiona Lowe. Just looking through Fiona's CV, she's had an amazing and winding career in a lot of different subject areas and disciplines and research centers. So we're really excited to have her here today. She got her Bachelor of Science from Caltech in Planetary Science in 1992, then moved on to get a master's from UW in Atmospheric Science in 1996. Then became an associate scientist at NOAA PSL for a few years working on the Madden-Julian oscillation. Then moved on to the National Snow and Ice Data Center in Boulder from 2000 to 2005, working on the North American monsoon. And then jumped ship a little bit, went to the Center for Australian Weather and Climate Research, working for the Bureau of Meteorology there from 2006 to 2008, developing seasonal forecasts for the North Australian wet season from different kinds of rainfall data, and then came back to the US working as a research assistant at Cornell from 2012 to 2016, but I guess sort of simultaneously was also a support scientist for Northwest Research Associates in Redmond, Washington, working on sandbar migration and shoreline erosion type work. And then fairly recently went back to go get her PhD, working at UW again, getting her PhD in atmospheric science. And this is, I think, where our interests align between the panel and her work is her PhD work was developing machine learning techniques to predict pollen, its evolution, and evaluate its impact on allergies throughout the United States, particularly using industry trends, so Google searches and Google trends to try and understand, how pollen is being distributed throughout the United States and be able to predict that using these machine learning techniques. So currently, Fiona is a postdoctoral researcher at UW with the Environmental and Occupational Health Service, continuing her pollen research, as I understand it, and we'll hopefully hear more about it today. But yeah, we're really excited. You have a lot of experience and expertise in a lot of different areas that the panel is excited to learn more about. So I'll hand it off to you. Thanks.
Yeah, thank you very much. It's a great honor to be invited today to talk to you about my PhD thesis. And I'm going to start off because can everybody see my slide?
Yes.
Okay, yeah, great. Yeah, so I'm going to just talk a little bit, because you're interested in climate and health, how I got to doing this. So as Dylan said, I'm basically trained as an atmospheric or climate scientist, and I've done a lot of work in many different areas. And I've always been interested in health, and actually even thought about switching fields. But most people switch fields because they don't like what they're doing in the old field, and that wasn't my case. So I never switched, but then I realized, oh, I could actually study climate impacts on health. And so about 8 years ago, I started really reading up about it and talking to people. And I realized that Dr. Jeremy Hess is right in my backyard. He's an emergency room physician, as well as having a master's in public health. And he's a professor at the University of Washington. He's director of the Center for Health and Global Environment. He has done a lot of work in climate and health, particularly related to heat. And about the same time, I took a 2-week workshop, a climate change and health research methods workshop. And this was in the Global Health and Epidemiology Department in Umeå University in Sweden. And this was my first experience with dealing with epidemiologists or health scientists. And it was really eye-opening. And at about the same time, Cecilia Bitz, which some of you probably know, she knew of my interest in climate and health. And she said, well, she brought to my attention the NASA and Health Air Quality Science team. And we ended up writing a proposal related to pollen, air quality, and health. And this ended up funding my graduate school and became my thesis. So today I'm going to talk about this, talk about forecasting pollen for allergy management. And as I said before, I worked with Dr. Jeremy Hess and Dr. Cecilia Bitz on this, and I'm now a postdoc in the Department of Environmental and Occupational Health. So what was my motivation for this? Well, pollen can cause allergic reactions in humans. And then pollen forecasts can provide an early warning for minimizing these allergy symptoms. So this is what I really wanted to do, was be able to help people that suffer from allergies. But as probably a lot of you know, research is never quite goes the way you want it to go and not quite linear. So I ended up spending some time trying to improve pollen data. I'll talk a bit about the problems that I encountered with the pollen data. So let me tell you about allergic diseases. So pollen is a major cause of seasonal allergies. This is also called allergic rhinitis or hay fever. And there's been many studies that have shown that days with high pollen levels are highly correlated to increased doctor visits, medication fills, and asthma-related emergency room visits. There's a dose response. If you've been following COVID, you probably have heard this term, dose response, which really means if you have more exposure, you have a more severe reaction. So in terms of pollen, if you have an increased pollen concentration, you have probably worse allergy symptoms. And then allergic rhinitis is also a risk factor for asthma, asthma being a more severe illness and sometimes potentially life-threatening. The impact of this is usually fairly underestimated. We don't actually know how many people suffer from allergic rhinitis. It's estimated up to 30% of the US population. Part of this is partly because people with allergies often don't go to the doctor. Besides the healthcare cost and financial direct cost, there's also indirect costs. Studies have shown that there's a lower quality of life, lower productivity, adverse school performance, and poor sleep associated with allergic rhinitis. And unfortunately, this can't be cured, but it can be successfully managed. And so how do you manage these symptoms? There's three main methods. I'm going to talk about two of them today. The first two are taking allergy medication. The second is behavior modification to avoid pollen. The third is immunotherapy. So with the first two, the ones that I'm going to talk about, to be able to manage these symptoms successfully, you need pollen information. But unfortunately, what we have now is not very good information. There's a lack of accurate information. So there's been a study, and it shows that popular media pollen concentrations differ from the actual observations. And really, this is because they don't consider regional variability. This was a study out of Canada and looked at the weather network. And in the US, two popular pollen forecasts, or ones that give pollen data, pollen information, pollen.com and weather.com. And for these, they either the model and data are proprietary, or there's no source listed for the pollen data or pollen forecast. And purely from my unscientific, observation of this data, it's not that great. So if it's not good, there's no way of knowing why it's not good, because we don't know anything about the data or the model. So what do we know about what do we know about the pollen data in the US? Well, we have the gold standard is data from the National Allergy Bureau. The National Allergy Bureau is run by the American Academy of Allergy, Asthma, and Immunology. So I want to point out here that this is a health organization, and this will be a little bit of an introduction to my experience with health data. So I have daily pollen concentrations. I have data from 2003 to 2018, although I have now updated 2020 data. I just got last month, but I haven't updated my analysis yet. I have 65 stations in the continental US and 38 different allergenic pollen types. So these are mainly run by, volunteer run by allergy clinics, these stations. This is an example of how they collect the data. Most stations use a Burkhardt air sampler, which is shown on the left here, and it sucks in air, sucks in all the air and aerosols and pollen with it on a sticky tape, and then the tape gets processed, and then a certified technician then sits and counts and identifies the pollen. And I talked to the technician at the Seattle station, and she said at the height of the pollen season, she spends a couple hours, 2 to 3 hours counting the pollen. So it's extremely time consuming, it requires expertise, and is very labor intensive. And unfortunately, this is not funded. So there's a convenience of sampling. And so there's actual limited spatial temporal coverage for this. There's many states which don't have any station at all. And there's also temporal coverage problems, which I'll get to in the next slide. But I do want to say in defense of these allergy clinics that the primary goal of the clinics is to help their patients. They're health professionals and not necessarily trained in the research of pollen or the best practices of data collection. Oh, and the other thing that also makes this very difficult to get this pollen data is each clinic owns the data they collect. So, so each clinic must give their permission for us to use their data. This is an indication of the temporal coverage issues that we have with the pollen data. This is an example of Atlanta in 2017. The x-axis is the day of year, and then the y-axis is the pollen concentrations. And the grayed out areas, grayed out lines are the days in which pollen is not collected. So you can see that the data is not collected on weekends. And this is, this is there's about 38% of the NAB stations that also don't collect on weekends. The Seattle station does collect on weekends, but the data is not collected in the fall and the winter, and approximately 12% of the NAB stations have this sort of collection pattern. And then unfortunately, we have almost half of the stations that do not collect data on weekends or in the winter. So there's a real issue with missing data. Okay, so yes, so the pollen data is in a way in its infancy. It's not up to the quality and the standardization that we're used to in meteorology. Now you have a little intro to the pollen data. Let's talk about the forecast, making a forecast from. So I'm going to talk about the simplest of forecasts, which is a pollen calendar, and then I'm going to talk about forecast of daily pollen concentrations. So what is a pollen calendar? This is a pollen calendar of Seattle. On the x-axis is the day of year, and the y-axis is the pollen, different pollen types, and they're ordered by abundance, the most abundant up at the top. And so pollen calendar is the daily mean climatology of pollen. So it's basically, if you want to make it's a first order forecast. So it shows when the pollen season occurs during the year for a specific location. So I produce these because, surprisingly, I could find only a few locations in the US that actually had pollen calendars. This is not very easy information to come by. So I wanted to provide an easy, clear visualization that's easy for people to understand when, where, and what type of pollen is in the atmosphere. So each pollen has a season, concentration ramps up, and then it gradually tapers off. And if you suffer from allergies and you don't know what you're allergic to, you can kind of look at this pollen calendar and figure out what pollen type you're most likely allergic to. So, so I've never been tested, but looking at this pollen calendar, I figured out that I'm probably allergic to cedar pollen.
Fiona,
Anyway, oh, yes, go ahead.
Sorry, I have a kind of a silly question here. Why are humans allergic to pollen at all? I mean, pollen's been around forever, longer than humans. I mean, why have we evolved to be allergic to it?
Yeah, so this goes into immunology, which I really can't seem to understand. And I've asked a lot of, I've tried to read papers, which is just beyond me, immunology papers, and I've asked allergists and I've asked some immunologists, and nobody's been able to explain to me how the immune system works. But basically, when you get an allergic reaction, your body is misidentifying the pollen and thinks it's something dangerous and tries to get it out of your system. And when it does that, it's reacting. It's what you call allergic symptoms, and it's reacting badly. It's basically, I think, your body not working properly. And there's all sorts of autoimmune issues, and
Right.
COVID, I think, is also associated with that. And so I don't understand it. It's way beyond my knowledge.
Sure.
Hopefully that's enough. Yeah.
Yeah, it makes sense. It's just interesting that that pollen's not a new thing, right? It's not something that humans developed that we decided that we're allergic to. It's just something that humans have always had to interact with, and our bodies just have never been able to process it, or most people's bodies have not been able to process it. As opposed to
Right.
like peanuts like or like peanut butter or whatever, we've sort of manufactured it in a way that might be more dangerous for humans. But anyway, I digress. I was just curious.
Yeah, and all the allergic pollens wind pollinated come from wind pollinated plants, mainly because the wind pollinated plants put out a ton of pollen. They're trying to beat the odds, whereas insect pollinated plants usually aren't allergic to humans aren't allergic to those.
It's interesting. Okay, thank you.
Sure. So yeah, so this is the simplest of forecasts. It's a climatology forecast essentially. And so yeah, so I wrote a paper, and it was out in 2019, and a lot of these, I think about 35 of the NAB stations is what I had back then, and I published pollen calendars for all of those stations, if you're interested. So now let me talk about the not so easy to make forecast, which is a forecast of daily pollen concentrations. So to my process of coming up with a model for this was to first think, well, how does weather and climate affect pollen concentrations? Here's a video. This is actually taken right outside the atmospheric science department. It's a western red cedar, and it is emitting a ton of pollen, so much it looks like it's smoking. And this happened a couple years ago on an abnormally warm, sunny, dry, windy Seattle day. And the pollen count that day was under the extremely high category of 944 grains per meter cubed. This was in the news. A lot of people were suffering. I was kind of not able to work for a couple of days because I felt so miserable. So there's been many studies that show that there's meteorological factors that affect the amount of pollen in the atmosphere. And this includes things like temperature, wind, solar radiation. These all cause more pollen to be emitted and then to stay aloft in the atmosphere for longer. And then the things like humidity and precipitation, they cause pollen grains to absorb moisture, become heavier, and then tend to come out of the atmosphere quicker. Although there's been a study that also shows that humidity or light precip can cause pollen grains to burst into many smaller pieces, and then you actually have more pollen grains. Your number concentration increases. So these, it's pretty nonlinear, some of these. The time scale of this happens is in the order of days. And then I also thought about factors that affect the plant development and its readiness to flower. So things like temperature, growing degree days. If you're a gardener or into horticulture, you might have come across this term. It's basically a measure of accumulated heat. So a plant needs to get enough accumulated heat before it starts blooming, and this prevents a plant from mistaking a really warm day in the winter as a cue to flower and risking damage by frost. And usually this growing degree days is calculated from the beginning of the year. So it's a sum over maybe a month or two. Things like water, temperature, humidity also are very important for the growth of plants. So if a plant maybe experiences a drought the fall before it's going to bloom, it might damage the flower or the buds that are about to grow and affect the amount of eventual pollen that it can produce. The photo period is also very important. The plants use the amount of daylight as a cue to flower. So even if a plant has enough heat accumulation, the growing degree days has reached its threshold, sometimes it will wait until daylight hours are long enough before flowering. So this is really interesting in terms of climate change, where we know that temperature will increase and these plants may reach their threshold of growing degree days sooner, but if the amount of light that they doesn't quite reach until later, it's not clear what will happen with the timing of flowering. Of course, plants use solar radiation to photosynthesize, so this is also very important. And then I've included vegetation indices in my model. This is technically not a factor that affects plant development, but is an indicator of plant development. Greening usually occurs. Greening occurs when leaves grow, and this usually occurs when there's flowering as well. So the time scale for this is days, months, seasons, and it could be lagged. So I took all these variables and put them in my model at different time scales and lagged. And I'm just breezing through this description of my model very quickly. If you have questions later, you can ask me. So I put this all in my model, and I used a machine learning random forest model. And previous studies of machine learning algorithms show that a random forest is good at predicting pollen in Spain and Poland. So I decided to use this for the US. And random forest is good at it reduces the risk of overfitting for input predictors. So I was able to throw in a lot of predictors for this model. So now that I have my model, what to predict? So I wanted to predict something that's useful for allergy management. So I went back to thinking, well, what are the common treatments for allergic rhinitis? First one is allergy medications. Well, these take a few days to be effective once you start taking them. And then it's important to actually take it before you get allergy symptoms. Because once you get allergy symptoms, it'll take stronger medication or longer for you to get your symptoms back under control. So I decided a 7-day forecast of the start of the pollen season would be really useful to let people know that the season is starting, buy the medication, get a hold of the medication, start taking it. And then the second common treatment for allergic rhinitis is avoiding pollen. So I thought that this is sort of like a weather forecast. You kind of look 1 to 3 days in advance and then decide, well, am I going to go outside? Should I not go for the run and spend time in the gym instead? So I decided to produce a 1 to 3 day forecast of high pollen concentrations. So I produced a forecast, and I'd like to point out here that this random forest framework gives me, I can produce lots of different models from this. So I produced a model for every important allergic pollen type in the US, and also for every forecast lead time, and also a different model for the start, forecasting the start date, and also for forecasting the high pollen days. So talking about forecasting for the start of the pollen season, we have to backstep a little. And how do you define the start of the pollen season? Again, I had to take this from a health standpoint, what pollen concentration does an individual start to experience allergies? So that is what I wanted the start of the pollen season to be. So this is where we collaborated with the CDC and the Climate and Health Group. And we just have this paper out, and Shibayu Saha was the lead on this. And it's the short-term physician visits and medication prescriptions for allergic disease associated with seasonal tree, grass, and weed pollen exposure across the United States. So what this means is Shibayu basically conducted an epidemiological study and look at the relationship between pollen concentrations and doctor's visits and medication prescriptions for allergies. So the hypothesis was what we know about dose response. If you have a higher level of pollen concentration, you'll get more severe symptoms and make people want to go to the doctor or get prescriptions for medication. So just give you a quick summary of the results. It shows that the increased relative risk at moderate levels of pollen concentrations. So this is significant because previous studies have only found that there are high levels of pollen concentration that have a health effect. So and all previous studies have just been location specific, and this included all of our NAB stations throughout the continental US. So I think we used 28 NAB stations, which matched with the location that we had health data. So I'm going to just talk a little bit about this table that's in Shibayu's paper, just to give you a taste of what it looks like to look at an epi study if you want to start reading health papers. So this is a table that shows the relative risk of health outcomes. Here is the risk of needing to fill a prescription for allergy medications for different levels of pollen concentration. So the relative risk is the risk compared to the risk at low pollen concentrations. So you assume that at low pollen concentrations, there's no risk of needing to fill an allergy medication prescription. So that's why the relative risk for low levels is 1. And then you see at moderate levels of pollen, there's a 1.04 relative risk. That means there's an increased chance, a 4% increase of risk of needing medications to be filled at the moderate pollen levels over the low pollen levels. So you can see there's a dose response. As you increase the level of pollen concentration, more people need allergy fills. So this was done for tree pollen, and you also for grass and weed pollen. The bolded dark numbers are significant, and the 95% confidence intervals are listed there. And then this is the relative risk for physician visits for allergic rhinitis, also split by tree, grass, and weed pollen. And you can see again the bolded darker colors show that at moderate levels that you have an increased risk.
Fiona?
Yes.
I'm interested in these confidence intervals. It looks like they get wider with increased pollen level, which is a little counterintuitive to me because I would assume that the higher the pollen level, the greater the signal. But is it because there are just fewer samples of very high pollen levels?
Yes. Yep. You're right on.
Okay.
You got it.
I see. All right. Thanks.
Yeah, and I also want to point out here that one thing I've noticed with a lot of the health papers I've read is they love tables. I think in our field we love figures and maps and plots, but they like tables. I'm just going to point that out as a side note. All right, so going back to how do I define the start of the pollen season, and to answer the question at what pollen concentration does an individual start to experience allergies, from Shibayu's paper, we learned that it was moderate pollen levels, and that's 50 grains per meter cubed threshold from that paper. So how about identifying the start of the pollen season? So here's an example of the cedar pollen data from Seattle in 2014. Time is on the x-axis, pollen concentration on the y-axis. And and the grayed out areas is where pollen isn't collected. So you can see that they actually started collecting pollen in late January, but there's actually 10 days in February where there is data is not being collected. So if we if we define the start of the pollen season as moderate concentrations, this 50 grain per meter cube level, then the start of the pollen season is soon to be February 29th. But you can see that right before that, there's a bunch of days that there's no pollen collected. So do we believe this start date? So missing data is a real big problem. And this is where I took a slight detour and decided I really needed to improve the pollen data. So since I already had a pollen model, I decided to use the pollen model to develop a reanalysis data set, a reanalysis pollen data set. So what I did was I have all the data, meteorological data, vegetation data, but not pollen data. So I use all those environmental factors, ran it through my model and predicted basically a 0-day forecast for the pollen concentrations to fill in the missing data. So what did that look like for this cedar pollen? So the green dots are the model prediction, and it's used to fill in for the missing observations. So you can see that there's a significant amount of pollen that is predicted on the days in which pollen was not collected. And so if you use the 50 grain per meter cube threshold, we then calculate the start of the pollen season as February 15th, which is 9 days earlier than if we just use it for observed. So this is great. So now we know how to define the start date, and we have some better data. But what we really want is the start of the pollen season, the forecast, the start of the pollen season. So I did this. I used my model and predicted the start of the pollen season with the 7-day forecast, which is what we decided would be useful for health. What's the skill? So I'm just going to present this results for Atlanta oak pollen. If you use climatology as your forecast, there's a mean absolute error of about 7 days. So if you're trying to get a 7-day forecast, a 7-day error is not very good. So what I did then was used 3 different data sets to train my random forest model and to see what the effect of these different data sets will have on the skill of the skill of the forecast. So if I used observations only, which is basically composed with a lot of missing data, I have to throw out a lot of data in that instance, then I get a forecast with this mean absolute error of 7 days, also not very good. And then a lot of studies linearly interpolate when they have missing data. So just to remind you, the Atlanta pollen data is not collected on weekends, so there's a lot of 2 consecutive days where there's missing data. So I linearly interpolated over those, and if there's more than 2 days that are missing, there's no linear interpolation. But this basically gets rid of all the missing data. So what does the model then forecast? It has a mean absolute error of 2.8 days. And then if I use the reanalysis data to train my model, then I get an even better number, better skill And so the forecast skill is most skillful when trained with reanalysis data set. Now, what if I want to forecast a 1 to 3 day forecast of the high pollen concentration? So actually, what I really want to do is forecast for moderate levels of pollen concentration, since Shubayu's research has showed that even at moderate levels, people have a health effect. But I did this work before Shubayu's results came out, so I'll just show you results with high pollen concentration levels. So this is the results from a 1-day forecast of high pollen days. And I use sensitivity as a way of looking at the skill. This is used in actually medical diagnosis testing for diseases. And it's a true positive rate. And in this case, it's the correctly predicted high pollen days over the actual observed high pollen days. And so as a benchmark, I compared my model with persistence being the forecast of today's pollen, using today's pollen concentration value as a forecast for tomorrow's. And that has a sensitivity of 0.83. So sensitivity of 1 means you're perfect. So the greater the number, the better. So with observations only, it's 0.92. With linear interpolated data, it's 0.89. And the reanalysis data is 0.93. So it's better than all the, it's the most skillful when trained with reanalysis data set. But yeah, so.
Fiona, how many years is this over?
I have 16 years of data.
16 years, and so you're training on the 16 years?
Yeah, 16 years, and then yeah, in 365 days or 366 days.
Okay, but I mean, so you train on 16 years, and then what are the forecast period over?
So, so actually, out of the 16 years, I took out the test data and the training data. So that's within the 16 years. So these are fake forecasts, really.
So they're fits more than they're forecasts.
I'm sorry, what was that?
They're fits, not really forecasts. Is that correct?
No, I'm making a forecast. I'm just forecasting. What do you call it? It's a hindcast. So I'm
right, but you could do a hindcast where you determined your statistical model from a training set of data, and then did the prediction on an independent set of data, or you could do hindcast where you basically use all the data to make your model, and then what you're really doing is in-sample prediction.
Okay, so the first one is what I did.
Okay, so again, how many years do you use for training, and how many?
Oh, I think, let's see. I think it's 13 years then.
And so then the forecasts are for 3 years.
Yeah. Yeah. Okay. So I'm just gonna. I'll finish up here, and you can ask me more questions. So just in summary, I developed a random forest pollen model that uses meteorology and vegetation as its predictors, and this can skillfully predict pollen concentrations. And these models perform better than a forecast of persistence and climatology. The US pollen data has a massive missing data problem, so I created a reanalysis data set, and this is really useful for improving understanding, analysis, and forecasts. And I was very interested in applying these forecasts to reduce adverse allergic reactions. So I want to thank NASA HACAS that funded this project, and all the National Allergy Bureau stations. But before I end, I'd like to talk a little bit, because I know you're interested in my experience with climate and health, some of the things I've learned working in this area. So be open to learning and using another language. Like another field always has different lingo, methods, tools, conventions, and standards. And so I felt like in the beginning, 80% of my time was just learning to communicate. And I found that a lot of the health work is done in just one location. They're really comfortable with temporal analysis, but not with both spatial and temporal analysis. Biostatistics are extremely good with small numbers. I think they deal with rare diseases often, so they have lots of tools and methods that I had never come across. And then health also uses qualitative analysis, which I had no experience with, and I honestly didn't have too much respect with before I learned more about it. But I've learned a lot about it, and it is a very useful thing, an analysis technique, and it's used in social science a lot too. And it's just one thing that I've learned. The challenges of working in climate and health is the biggest one, and you've probably seen a little bit of this in relation to my pollen data, is the availability and access of health data. So a lot of health data costs money. There's privacy concerns. So due to HIPAA laws, you have to prevent the data, being able to figure out who a specific individual is. So there's, some sort of, you can't, sometimes the details are a little murky. And the data is sometimes limited. If you apply for a data set, sometimes they say you can only use it for a particular project, and maybe it's time limited. You're only able to use it for this proposal and maybe 5 years later. And then many of you probably work doing interdisciplinary work, and this requires commitment. You have to commit to learning how to communicate, learning everything else that the other field is about, and stepping out of your comfort zone, take away your ego, know that you're just going to learn a bunch of stuff, and try and also communicate without lots of jargon. I once wrote in a paper, climatology, and the reviewer came back and said, this has nothing to do with climate. And I was like, oh, I can't use climatology in the way we use climatology. You have to use something like long-term mean. And then, of course, there's funding issues, as with everything. Whichever field you're trying to apply for funding in, they always think that the other field should be the one funding you. And then this is just a quick little list of what I think health scientists and professionals need from us. Is in no way exhaustive or complete. But most importantly, I think they need easy access to data with no jargon, maybe a list of pros and cons of a data set, biases. I once had a Washington State Department of Health scientist come talk to me, and she said, oh, I was looking for temperature data, and I spent one morning just trying to find it, and I didn't get anywhere, and so I gave up, which is exactly not what you want to hear. Health scientists also like the high spatial resolution. They usually deal with things on the county level. Sometimes if it's really good, it's zip code level. So they aren't used to using lat longs or satellite swaths. So anyway, so that's just quick and dirty. I just threw together this slide, and hopefully that gives you an idea of what I think. And I'll stop here, and I'll be happy to take any questions. Thank you.
Fiona, I'm really curious about your reanalysis. Could you explain that a little more? That seems to be kind of, a key part of a lot of what you did.
Yeah, it did. Well, I didn't start off trying to do it that way, but it did end up being key because there's a lot of problems with the pollen data. So yeah, I sort of glanced through it, but I have the random forest model, and it takes a lot of the environmental inputs, and it can predict pollen concentrations from that. And so I basically made a 0-day forecast. So if I have all the environmental information for that day, I can predict the pollen for that day. Is that, I'm not quite sure if that's answering your question.
Well, I'm trying to get a sense of how, if you put that into a forecast model like this and get an improvement, are you just testing? And there's a sense in which if you constructed all the data from your reanalysis and then did a forecast, you have a perfect model that's now generating your forecasts. It's not necessarily quite a fair test.
Oh, right. Yeah. So, sorry. My reanalysis data set is actually, I use observations when they're available. And when there's missing data, I'll use the model output.
Do you have, are the missing, I guess this kind of is related to a comment you made, but I guess I was wondering, so you constructed your model from just the one location, right?
Yes.
So from a climate perspective, you wouldn't normally do that. So I was curious why you decided to do that as opposed to take advantage of other stations in the area where you might have spatial correlation in the climate signal and also spatial correlation in the pollen data, so that the pollen data in other locations might be used to fill in your missing data. I mean, if you did like an EOF reconstruction as maybe an overly naive approach, then maybe you would have something that was entirely independent to your model.
Yes. So, so there's a couple. Yes. Good point. Great question. So, yeah. So I started off predicting just for one location, and then I did look at using a regional model, and that. So I used grid cells around the station to predict, in addition to the grid cell in which the station was located, and that did improve the forecast of the model. And then there is a point at which, and it's not totally clear what the spatial scale is where pollen is correlated. So there's, I mean, the number of stations I have is sometimes pretty far apart from each other. There's not many locations where there's a lot of stations that are close by, and some of these stations are actually really not that great, so they're not a ton of reliable data. And then I did actually try and run I used stations from all over the US, and I did run a gridded model. So this is what it might look like for oak pollen over the oak pollen season. And so, of course, it's hard to validate how good this is because I don't have too many observations. But it turns out that it looks like it gets the temporal shape well, but it doesn't get the magnitude very well. So.
Fiona, sorry, just looking at that map, I have no idea if this is possible, but is it possible to measure pollen with satellite measurements? I mean, once it's at high enough concentrations?
Yeah, definitely we thought about that, but I think it's I have not looked, but it's probably not so easy to see. Pollen grains are of lots of different sizes, and you have, of course, you got to see through clouds, and you've got to know what else is in the atmosphere to make sure that it's not, that you're not picking up other aerosols besides pollen. So,
right.
I've talked to a lot of other people and thought, but just bounce that idea off. But none of us have thought that it's actually feasible.
Hi, Fiona. Thanks for the interesting talk. I think something that I would be interested in knowing is in your model, how important the different environmental factors were, because if you're going to make a predictive model, we're pretty good at temperature and maybe not so good at precip. So could you just give us a sense of the different loading in your model?
Yeah, so this is the problem with machine learning is it's often hard to interpret data. But the random forest model does, as one of its outputs, give you it ranks the importance of the predictors. And so I'm in the middle of teasing that out because, of course, a lot of my predictors are correlated with each other. So I also want to be careful about which ones really are the most important. But it turns out for oak pollen, and a couple other pollen types, I can't remember which ones. It looks like, yeah, temperature is the most important. Solar radiation is also very important. But my goal is, yeah, to, once I've teased out, find maybe the top 5 to 10 of these variables is then maybe to make a non-machine learning model so that then it's easier to interpret using those 5 to 10 most important variables.
It was on a 1 week lag, right? That's what you.
Yeah, the 1 week lag for the start of the pollen season.
You might have mentioned this, but is there real-time data available? I mean, could you stick this model on a web page somewhere and then sort of track it and see how it does?
Yeah, that's actually another big issue. I developed this with the assumption that I would be able to get daily updates of pollen concentration. But as it is, I get, well, in the last 5 years when I've been working with this data, I've gotten updated with the data once a year. So it's not, it's right now it's not feasible. We have a proposal in with NASA to actually try and make this model operational. But the thing is, I also developed a model that, and I didn't mention this. So with my model, I can include pollen as a predictor because there's a good autocorrelation today. Today's pollen is a good indication of tomorrow's. But I also produced a model which doesn't include pollen observations, just purely because this data wasn't available daily. Yeah, like I said, this data is is at its infancy.
So
Fiona, does your model
go ahead?
Does your model include information about the biological life cycle of the pollen producing plants? In other words, whether a certain time of year is going to have a bigger impact, but you also want to know what happened before that particular day.
Yeah, and so that's hopefully that's in the model. It's I have all these variables lagged by different amounts, and different plant types will obviously react differently, which is why I have to make a model for each different pollen type.
Hi, Fiona. This is Mike Patterson. I'm wondering a couple questions regarding funding. The first one has to do with the insufficiency of access and collection of the pollen data. And what do you think are the pathways for improving that over time? Are there funding sources out there to support that? You mentioned work being supported by NASA, I guess, on the modeling end. What about on the observational end?
Yeah, we're working. The CDC Climate and Health Group that we've been collaborating with, they're really, a couple people in there really interested in actually moving this forward, this collection, getting a good pollen data set. And it's difficult because, as I said, right now there's no funding for it. I guess it used to be that this, the PPAI, the Allergy and Immunology organization, they actually had big pharmaceuticals donate money, but then I think that wasn't allowed anymore. So once that went away, I think a lot of stations also went away. I know in Europe, I think the Swiss, Germans, and then I think Japan also has a pretty good observation network. And the Swiss have automated pollen collection and identification machines. And that unfortunately they're super expensive right now. I think they're like $200,000 to $500,000 per machine, you know. And so if you want a whole network, that's really expensive. And they seem to perform pretty well. But I don't know. If you have ideas, I'm listening.
Right. Well, I was wondering how, just in terms of on the health agencies, if there's interest there in supporting these kind of networks.
Yeah, we're hoping maybe the EPA would, I think, makes the most sense of somebody be interested. But you know, so far we haven't maybe talked to the right person or yeah, gotten the right ear to listen to our pleas.
I mean, have you thought of private kind of companies that might be interested? You know, somebody, you go to them and say, well, here's a model you could predict on an app if only we had the data to input to the model.
Yeah, that would be great. But the NAB data right now, I think at one point, maybe 10, 15 years ago, they gave the data pretty freely, and some company made money off of it. And I think the NAB didn't really like that. And so now they have this big condition that they're really, you can only use it for research. And so, so if a private company wanted to do this, they'd have to set up their own, you know, collection network, I think.
This is the
I think
top
we
of
also want to. Oh,
Yeah.
sorry. Go ahead, Jenny.
No, go ahead. I was just gonna say it's the top of the hour, so if we have one last question, maybe Dylan. I don't know what you were gonna say.
Yeah, I do have a question. I was just gonna make a comment too that I think we probably want to try and promote free and fair use of data and not go after private companies if we can avoid it. But I mean, if that's where the funding is, that's where the funding is. But maybe one more quick question. Your model, so you only have 13, you said 13 to 16 years of data. I'm wondering if your model has interannual variability trained into it enough to matter. So like you have a start of the pollen season every year, and there could be interannual climate variability like INSO that could, you know, drastically change the start of the pollen year, depending on where you're at and throughout the United States. And I'm just wondering if you have enough. I mean, always want more data, but I'm just wondering if your model might be able to take that into account at all.
Yeah, like I think it. Yeah, I think it can. You know, this is the beauty and the aggravation of machine learning is it's kind of a black box. You throw everything in and something comes out, and you assume it's right, you know, but you don't really know the inner workings. But yeah, you're right. Like I don't think 16 years is enough data. And a huge limitation of machine learning is it can't predict outside of what data you feed in. So if, for instance, you know, climate changes and you're in a different, you know, total different ecological regime, right? Your plant is in a, then like it won't be able to forecast that. So actually, a good example is we had a big heat wave that you might have heard of in June this year. And there was a lot of actual plant damage. You could see that there's plants that are scorched brown. And in June, a lot of the cedar pine buds are beginning to form. And so if those got damaged, then this coming spring, there might be less pollen. So this might be where the, you know, this is too hot. Usually everything else, all the studies have shown previously that with an increase in temperature, increasing the amount of pollen in the atmosphere. But in this case, I suspect that it's going to be too hot and we're actually going to decrease the amount of pollen in the atmosphere. But
I think that'll wrap up today's webinar. So I think, thank you so much, Fiona. I want to give you a round of applause from everyone. And we are also looking forward to, or looking for some webinar topics to tackle for the next few months. So if you have any, feel free to email myself, Hyen, and John about them, and we can possibly reach out to some folks. And I'm not sure if this is going to wrap up the climate and health theme or not, but hopefully, if not, I think we might have one more talk. So again, thank you so much, Fiona, and hope you guys have a great rest of your afternoon.